Morning everyone. Here we are all alone in an empty classroom. I hope all of you are maintaining your social distancing and take the COVID seriously, because the latest studies by Imperial College, I believe, from UK claim that the expected number of fatalities in the UK could be as high as 250,000. And we don't have predictions for the US, but then those numbers don't seem very nice, so do be careful. We are streaming live. I don't know if you're watching, but if you are, Vedant is over here. You can ask your questions on Piazza. He's monitoring it, and I will answer your questions as they come up. So anyway, we're going to continue with our series on recurrent neural networks. This is the last lecture in the series, and specifically we're going to continue on the topic of sequence-to-sequence models. Today we will be talking about attention models. Now here is the sequence-to-sequence model problem. You have some input sequence x1 through xn, and you want a model that can process this input and produce as an output a different sequence y1 through ym. Examples of problems like these: speech recognition. You have a sequence of audio samples going in, and you want a sequence of words to come out, or maybe a sequence of phonemes or character sequences. Whatever it is, you have one type of data going in, sequential data going in, and a different type of sequential data coming out. Or machine translation. A word sequence in English may go in, and a word sequence in French may come out. The number of symbols going in does not have to be the same as the number of sequence symbols coming out, which means there doesn't have to be any notion of synchrony between the input and the output. You may not be able to assign distinct times at which the output symbols come out. We saw two different variants of this problem. The first one, where we do have a notion of an alignment. For example, in speech recognition, speech samples go in and words come out. There is order correspondence between the input and the output. So the order of words in the output is the same as the order of words in the symbols and the samples in the input. And so there's the notion of an alignment, where one might be able to say that this word I comes from this portion of the audio, so it should be aligned to this region. The word 8 should perhaps be aligned here. The word and should perhaps be aligned here. The word apple should perhaps be aligned here. So you have a notion of an alignment of the output to the input, and each output symbol can be aligned to some portion of the input data, input sequence, and the alignment is going to be sequential. Now you have the other kind of problem, like in machine translation, where you have some sequence of words going in and a different sequence of words coming out. In this case, there is no correspondence between the order of the output symbols and the order of the input symbols. So here, for example, the English is I ate an apple. The German is Ich habe einen Apfel gegessen. Here, 8 is the second word, whereas when you go to the German side, 8 actually splits into 2 and becomes habe gegessen. So there's really no notion of one-to-one correspondence between the input and the output, or even an order correspondence. In the last class, we dealt with the aligned case, where you have an order correspondence between the input and the output. So these were the CTC models. The input and output sequences happen in the same order, and although they may not be time synchronous, in the sense that you may not have one output at each input instant, you do have order correspondence where the outputs occur in the same order as the input, and you do have a notion of an alignment. So the first output may be aligned against some region of the input, the second output may be aligned against the next segment of the input, and so on. So an example of this was speech recognition. The input is speech, and the output may be a phoneme or a word sequence. Today we are going to look at the other kind of problem, where we don't have this kind of order correspondence between the output and the input. The output may in fact have more symbols than the input, and you don't even have a notion of a one-to-one correspondence. Consider this. This word 8 actually becomes two words, habe gegessen, in the output, And these two words are split with many other symbols occurring in between. So there is the notion of correspondence completely breaks down. So how would we actually model this kind of sequence-to-sequence conversion? Before we continue with this problem, let's quickly recap another problem that we did discuss in the last class, in the previous classes, which is that of predicting text. Here you have a simple problem. You are given a series of symbols, which could be characters or words, and you have to predict the next symbol. So you might have, say, words W1 through Wn, and then you have to predict what the next word in the sequence might be. So here are a couple of examples. You might say 4 and 7 years, and then you must predict what the word in this location is, in this location indicated by the question marks is. Or you might have these characters A, B, R, A, H, A, M, L, I, N, C, O, L, and you must predict what this final symbol is, what this final character is. So you're given a sequence of words or characters, you must predict the next one. What we are really doing over here is to learn to model language. We are learning the sequential structure of language. This is language modeling. And if we are doing this using recurrent networks, we would have a model such as this one. You would have a model that's going to take in a sequence of symbols and predict the next symbol. So after seeing W0, it must predict that the next word is W1. After seeing W0 and W1, it must predict that the next word is W2. After seeing W0, W1, and W2, it must predict that the next word is W3, and so on. In general, after observing inputs W0 through Wk, it must predict Wk plus 1. So in terms of implementation, here's what it would look like. The inputs are words. Obviously, they must first be converted to some kind of numeric format. So you're going to assume that there's an ordered vocabulary. And so now each word can be represented as a one-hot vector. And so the input words are now presented as one-hot vectors. And these one-hot vectors are projected down to some lower dimensional embedding. We saw how some techniques for how such embeddings, how these projection matrices that compute these embeddings might be computed in the previous class. So these hidden units could be one or more layers of LSTM units. And at each time, the output of the hidden unit is going to go into a final layer, which will produce a probability distribution over words. This one is going to, so what we are producing, although I've actually indicated words over here, what you would actually be outputting at each time is the probability distribution for the words at the next time. And the parameters of this entire model, which models language, must be learned through backpropagation. So since the intention here is to be able to predict which words are most likely at the next time, given all the words we've seen until now, the way we will train it is to actually train it to predict the exact next word. So here the training data are simply going to be sequences of words, sentences. And now you'll be presenting the input as one-hot vectors, which will be projected down. At each time, you have a probability distribution over all the words in the vocabulary. And the target is going to be the next word in the sequence. So here, at time 0, the target is going to be W1. That's what you want to predict. So your ideal output in this case must be a one-hot vector which peaks at W1 and must have 0 values elsewhere, or at least it must make W1 the most probable word in the vocabulary. So this would be the target. And so also at each time, you would be producing outputting a probability distribution, which actually represents the probabilities of all words, the probability of the, which actually represents the probability of every word in the vocabulary occurring at this specific location, given that all the previous words in the sequence were the ones below. So at time 3, it's going to produce the probability of that the fourth word is going to be, say, the or a or an, given that the first 3 words were whatever, A, B, C. So the divergence you would compute is going to be the divergence between this sequence of probability distributions and this target sequence of words. And in this setting, if we use the cross entropy loss, the cross entropy as your Kullback-Leibler divergence, which gives you the cross entropy loss, we saw that the actual divergence can be decomposed into the sum of the cross entropies at each time. And that in turn decomposes is to the negative of the sum over all time of the log of the probability assigned to the target word at each time. And so this divergence we would minimize, so the parameters of the network would be trained to minimize this divergence using backpropagation over time. So this is how you train the model. Now, once you train the model, you can actually use it to synthesize, generate word sequences. On a trained model, you would provide the first few words as one hot vectors. And then say you were providing W1 through W3. At time 3, the network would produce output a probability distribution over words that could occur at time 4. And so now here is the key piece. The reason we are going over this portion of the lecture is that this is very relevant to what follows. So what happens at time 3 over here? At time 3, the output that's being computed, what has been given to the network so far are these words, W1 through W3. And what you are producing is the probability distribution for the words that could occur at time 4. So you would actually get, if your vocabulary consisted of V words, you would actually get a V length vector, and each component of the V length vector is going to be the probability of a specific word. So if your vocabulary is say A and say B and so on, the second entry over here would be the probability that W4 equals N given W1 through W3. So at each time, you are computing the probability of the next word given all the words that have previously occurred. So once you provide the first few words, say you input W1 through W3. At W3, you'd get a probability distribution for W4. You draw a word from that distribution. And now that W4, that new word, becomes a reality because you've already chosen the word. And that word is going to be treated as the next word in the sequence, which is input to the network. And the network is now going to produce a probability distribution for words that will occur at time 5, from which you would choose a word and go on. You'd keep producing words in this manner. How long would this production continue? When would we stop? So here we have to briefly digress into how we treat the starts and ends of word sequences. Now, a sequence of words by itself does not indicate whether this sequence was a complete sentence or not. So for example, if you just have this sequence 4 score and 8, just looking at 4 score and 8, you cannot say whether these 4 words occurred in the middle of a sentence, or at the beginning of a sentence, or at the end of a sentence. Are these the first four words of the sentence, or the last 4 words of the sentence, or somewhere in between? Just looking at the words, you cannot say. So to make this explicit, we are going to introduce 2 new symbols to our vocabulary. The first one is a start of sentence symbol. The second is an end of sentence symbol. And to see how these would be used, let's look at some examples. If I saw a sequence of words 4 score and 8, there are no start or end markers. So this is clearly a sequence of words in the middle of a sentence. Whereas if I saw something like this, a start of sequence 4 score and 8, because the first symbol here is the start of sequence symbol, this means that this sequence, these 4 words represent the first 4 words in a sentence. These are from this beginning of a sentence. Similarly, if I saw a sequence of words 4 score and 8 followed by the end of sequence symbol, then This clearly indicates that this is where the sentence terminates. So these 4 words represent the last 4 words in the sentence. And if I saw something like this, start of sequence 4 score and 8, end of sequence, that means that these 4 words represent a complete sentence from beginning to end. Now, we may not always explicitly use the start of sequence symbol in situations where the start of the sequence is obvious. It may not be explicitly represented. Also, as an engineering device, often instead of using 2 distinct symbols, we may just use 1 symbol to represent both the start of the sequence and the end of the sequence. Now, continuing. So, say we are drawing words from our language model. When do we stop? We would continue drawing words until we draw an end of sequence symbol, at which point we know the sentence is complete. You're going to stop drawing words further. You might also have other kinds of criteria to terminate generation. For example, you might have a maximum length, or you might have just arbitrarily choose to stop producing words when you encounter, say, a magic word like Yeti. But if you're really speaking of complete sentences, then where you would stop is when you actually finally drew the end of sequence word. So we've sort of gone over the problem of learning a language model and how to generate text from this model. Both of these are relevant to what we're going to speak about next. So let's return to our problem, which was the sequence to sequence generation problem, where you have one sequence of symbols going in and a different sequence coming out. Now, if you have a problem like machine translation of language, then the sequence that goes in is going to be in one language, the output sequence is going to be in a different language. Now, this process is actually very similar to predicting text, but there's a crucial difference in that the vocabulary for the input sequence is different from the vocabulary for the output sequence. So the model that we will use for this problem is this one here, what we call the delayed sequence to sequence model, where you have a sequence going in and a sequence coming out. And the manner in which we will do it is that we have one part of the model which first processes the input and produces a hidden representation for the input. So here's a little bit of pseudocode for it. This is just for reference. I won't talk about it too much, but you'd be stepping through the input and continuously computing these hidden representations. Observe that you're not actually computing the output. All you're interested in is the hidden representations. And when you're done processing the input, the final hidden representation is what is now going to be used. This is now passed on to the second component of the network, which will use it to generate the output sequence. So here is the complete pseudocode. This portion processes the input and produces the hidden representation at the final time instant. And then the second portion of the network is going to use that as the initial state for the hidden representation, the hidden layers. And then subsequently, you'd be stepping through time. And at each time, you're going to be just processing the hidden representation. And based on the hidden representation that you got from the previous time, you get a probability distribution over words. And the actual output word is going to be drawn from this probability distribution. You would continue doing this until you encountered an end of sequence symbol. Now, this one over here, again, observe, is not generating a single word. It's actually outputting a probability distribution. The actual word is drawn from this distribution. Now, there's a problem with this model. And the problem is this, that once I begin drawing words, the word that I draw at this time has no influence in the word that I draw the next time. So let's say I've got some hidden representation, and then I begin producing words. Now, the only information that is being passed from time instant to the next time instant is the hidden representation itself. The word that was actually produced at any time is not considered when you compute the hidden representation for the next time or the word for the next time. So So this leads to a problem, right? And the problem is this, that if I say I had a distribution and I produced the word I, or drew the word I over here, I drew the word had over here, I drew the word an over here. Then when I'm drawing the next word, since the word that has been output is not actually fed back over here, this situation, as far as the fourth word is concerned, is no different from this one over here, where I draw I had and a. Now clearly, if I said I had an, then apple is a very plausible next word. Whereas if I said I had a, then the next word really shouldn't be the word apple. But because this is not being fed back, all that's happening is that you're looking at the hidden representation. Then in both cases, the probability that you will draw the word apple remains identical. So in other words, you're not really, the fact that you're not considering the previous word in deciding what the next word must be causes a problem. So we're going to change this model. We are going to actually explicitly have this word go back in to inform the drawing of the next word. And so here is the model that you have. It now becomes a two-component model. First, the input sequence is processed to produce a final hidden representation, and then this hidden representation is now going to be communicated to the second component, which is a self-referencing network, where at each time the word that's actually drawn is going to go back as an input to the network. So here's how this simple model will work. We're calling this the simple translation model because, as we will see, the model will actually get more interesting and more complex later in the lecture. So the input sequence, so let's say you are trying to translate I ate an apple. The input sequence would feed into a recurrence structure. And since this is a sentence, as soon as the end of sentence marker is encountered, the final you know that there are no more words to process. And so the final hidden representation over here is going to be treated as the activation that stores all of the information about the sentence. Subsequently, this information is going to be passed on to the second recurrent network, which uses this hidden representation as an initial state to produce a sequence of outputs. And the output at each time becomes an input to the next time, and output production will continue until an end of sequence marker is produced. So for example, after having produced the input process the input until here and produce this hidden representation, to produce the output, this one is going to be treated either directly, or the dimensionality may be transformed using some matrix, so some transform. So for instance, if the final hidden representation is h of t, let me call this the h input. This is going to be treated either directly or after some processing as the initial hidden representation of the output. And we can have all of these different options. H output of -1 is simply h input of t, or this could be some matrix times h input of t, where the matrix serves the purpose of adjusting the dimensionality and is a learnable parameter, or it could be any other odd function of t. Typically, we're going to use either something like this or something like this. So we won't actually spend any time on the specific manner in which the final hidden representation is converted to the initial the final hidden representation of the input is converted to the initial hidden representation of the output. We're just going to assume that the two are identical. So once that is done, this is going to be passed on along with an input, which is the start of sequence symbol, to the output portion of the network. And this is going to produce a word. And when I say produce a word, it's going to produce a probability distribution from which the word is drawn. And that is going to be fed back in along with the hidden state here to produce the next word, and so on, all the way until, yes?
Someone is saying they can't see where you're pointing towards.
Can they not see with the laser pointer?
I'll
Just ask them. So let me just continue, right? So I'm going to assume that you cannot see the laser pointer, so I will also explicitly state what I'm pointing towards. So here at the output, which is the yellow portion of the graph, the production will continue till you produce a final end of sequence symbol. Now, observe something interesting over here, that if I drew, in this example, I've drawn the word ish at the first time instant. And this word ish is now fed back into the network at the second output time instant. Now, if I had drawn a different word, remember what you actually get at the first time is a probability distribution from which you get picking a word. So if you chose a different word, a completely different word would now be input to the network over here, which means that the probability distribution at time 2 is going to be different from what it would be if I had chosen ish. And this means the rest of the production is also going to change. So because you're explicitly considering the words that have been drawn so far and producing the next word, you're actually sort of you're making it sensitive to the specific set of words drawn, and so you can expect consistency over the words drawn. Now, the examples that I've shown the figure that's shown on top over here in the slide with only one hidden layer. In practice, you can have any number of hidden layers like the figure at the bottom. But since I'm only using these for illustrations, I'm only going to show one hidden layer in all of my figures. But you must assume in your mind that the number of hidden layers could be any number in the model. So here is a pseudocode for the production. And so this is the top portion of the code shows the processing of the input. The hidden representation at the final time becomes the hidden representation that is going to be, becomes the representative of the entire input, and that is passed on as the initial state, initial hidden state for the output, as shown by the snippet of code in the middle. And that is now passed on to the output stage of the network, where at each time the hidden state and the previous word, the initial word is said to be the start of sequence symbol. So at each time, the hidden state from the previous time and the word drawn from the previous time are passed into the network to compute a probability distribution over words at the next time. So observe that because now y is also being passed in along with h to the recurrence, the y out is also being, well, this should have really been, yeah, y out is the drawn word, right? So because the drawn word is also being passed in along with the hidden state to the recurrence, changing this one, drawing a different word at time t minus 1, will result in a different output at time t. Now, I've been using words like the input portion of the network and the output portion of the network. We have better terminology. The portion of the network that processes the input is generally called the encoder. The job of the encoder is to analyze the input and encode the input into some hidden representation. And the portion of the network that uses this initial hidden representation generated from the input to produce the output is called the decoder. Now let's take a closer look at how this is done. Now, in all of my models, in all of my figures, I've just shown the words going in directly. In practice, the words are not going to go in directly. The words are actually going to be, the words are always represented as one-hot vectors. And these are going to be projected down into embeddings using some projection matrix. And because the input and output vocabularies are different, you expect the projection matrix for the input in the encoder, which works on the input sequence, is going to be different from the projection matrix that works on the words, the output words in the decoder. Now, I won't explicitly show these projection matrices in my figures either, but you must always assume that these are always present, and these have either been pre-learned or are being learned as part of the model. Now, what does the network actually output? We are going to go back to this notion of probabilities. So let me see if I can explain this properly. So I have my encoder, and the encoder is going to see my sequence of input words W1 through WT. So then this goes into my decoder, and my decoder sees at the initial time the hidden representation produced from the input sequence and the initial start of sequence symbol. So what is being produced over here? What is this probability distribution? This one is actually the probability distribution of the words, let me call this the output words, at time 1, given, let me put a superscript here to represent their inputs, given the entire sequence of input words and the start of sequence symbol. So observe that these are all the things that have already gone into the network. So you have the entire sequence of input words and the start of sequence symbol that have gone in. This is the output produced. This is what the network produces at the first time instant. I'm going to, in the slides, I don't actually explicitly represent the start of sequence symbol because, as I said, this is often implicit, and we may not need to represent it. But the point is this, that at any time, so to continue this, let's say I drew a word. How am I representing this? I'm calling this O1, right? So let's say I drew a word O1 out here. Now O1 goes into the network at time 2. So what is this output over here? This output is going to be the probability that the second word in the sequence is the probability distribution for the second word in the sequence given the entire sequence of inputs and O1, because O1 has been produced. So this is at the next time, let's say I have drawn some word O2 over here. O2 is also being input. So now at the next time, the output of the network is going to be the probability distribution over words given the entire sequence of inputs and the sequence of outputs that have been produced until time 2. So in general, at any time k, this output y, which I'm representing using y, using the standard notation that we've been using in the lectures, this vector of outputs is going to be the probability, the set of probabilities, the vector of probabilities for all the words in the vocabulary given all the input words and the output words until the current time. And so the next word is actually being drawn from this probability distribution, and that drawn word, which is now going to be fed back into the next network. And now this becomes part of the conditioning variables, and what is actually output is the probability distribution for the next word given everything including this word. And this goes on until the end. Now, Here is the overall process. At each time, the network produces a probability distribution over words given the entire input and all the outputs until that time. And a word is drawn from this output distribution and is provided as input at the next time. And this continues until an end of sequence symbol is produced. So if I were to write this as pseudocode, we've actually seen this before. Once we compute the hidden representation from the input, at each time you're going to be feeding the previous hidden state and the last word drawn to the recurrent network, and it produces a probability distribution over words. And to compute the next word, you are drawing a word from this probability distribution. Now, what is this magic business of drawing? I've just said I'm going to be drawing a word now from the distribution. What do I mean by drawing a word? Now, to figure out what we really want to do, we must go back and consider what our objective is. Now, our objective is to translate the input word sequence to an output word sequence. So you've given a word sequence in English. You want to produce a word sequence in, say, French. So now, if I produced any given word sequence, I actually can, what I have done is draw a sequence of words from a probability distribution. At each time, for each word, there is a corresponding probability assigned to the word by the network. So at time 1, for the word O1, the probability assigned to the network, conditioned on everything until then, is going to be the corresponding component of the output probability vector. So also at time 2, the probability assigned to O2 is going to be whatever the corresponding component of this vector is, the probability vector at this probability vector output at time 2 is. Now, if I multiply all of these probabilities, what do I get? Now, observe that y1 is the probability of, let me erase this. Observe that y1 is the probability of O1 given W1 through WT. These are the inputs. Y2 over there, Y1, O1, right? So I'm not really sure. Okay. The indices here are somewhat different from on the slides. It's going to be the probability of O2 given W1 through WT and O1. Y3 is going to be the probability of O3 given W1 through WT and O1 and O2. So when I multiply these three, Y1 times Y2 times Y3, this is going to be probability of O1 given W1 through WT times the probability of O2 given W1 through WT and O1 times the probability of O3 given W1 through WT and O1 and O2, and so on. So this product, as you can see, is simply going to be P of O1, O2, O3 given W1 through WT. So clearly, the sequence of the product of these probabilities is going to be the probability of the output sequence given the entire input sequence. And when we are performing machine translation, what we really want to do is to output the most likely sequence given the input. You're given some English sentence. You want to find which French sentence is the most likely translation of this English sentence. So you want to produce the word sequence for which this probability is highest. In other words, you want to draw the word sequence such that the product of their output probabilities is highest. Now, how exactly can you do this? There's one simple solution. At each time, you can simply remember you want to find the word sequence such that the product of their output probabilities is maximized, right? So why not simply draw the most likely word at each time? This is the greedy answer. You just select the most probable word at each time instant. So in that case, if you go back to our pseudocode, this draw function just simply gets converted to finding the word for which the output probability was highest, the argmax. The problem here is that simply picking the most likely word at each time is not guaranteed to give you the word sequence which is most probable. Now, this may seem kind of odd, but then let me explain with an example, right? So what can happen is that if I choose the wrong word at any time, then although that word is very likely at the current time, it may cause the network to become more confused at the next time or at some time in the future. And so overall, the overall probability over the entire sequence of words could be lower than what we would get if you chose a different word at the current time. To see an example, let's consider this. Here's a hypothetical example. Let's say recognizing English speech. The input is speech and the output must be text. So let's say at time t equals 0, the word he was the most likely, so you chose he. At time t equals 1, the word knows, so there were two words, NOSE and KNOWS, and they're pronounced pretty much the same. So the word knows might just serendipitously be slightly marginal, it might have a marginally higher probability than the word KNOWS. So you've drawn knows. But then he knows is a really odd construct. So given he knows, what is the next word? You can't really be sure. So the network is probably going to compute some kind of a low probability for all words, something closer to a uniform probability distribution, because this is such a strange construct. On the other hand, the word KNOWS might have had a lower probability at time 2, at time 1. But when you say he knows with the word he knows, just to be clear, then this is a much cleaner construct. And so now the network can be is more clear about what is happening, and it would produce a more certain probability distribution for the word at the next time. So for example, in this case, the probabilities of all words may be somewhat low, whereas if you chose knows, then it's going to assign a small subset of words high probabilities, and the rest of them are going to have very low probabilities. So now if you drew one of these words for the third time, the product of the probabilities, although knows by itself was more probable than knows, the product of these three probabilities can actually end up being lower than the product of these three probabilities, because W2 over here had a very high probability, whereas over here all of the words had low probability. So basically, the fact that you chose the wrong word over here greedily ended up affecting the kinds of probabilities that you'd compute in the future, and ended up resulting in an overall lower probability sequence. And this, in fact, but then, how do we know a priori that we should be choosing the word KNOWS and not NOSE? Before you actually look at before you actually process that through the network and consider the next probability distribution, you do not have any way of knowing a priori which word will lead to the more promising future. Should we draw knows or knows? Now, in this particular example, it might seem obvious. Just put it into the network and you will know, right? The problem is that the effect might actually not be in the immediate next word. It could be way down the line. So for example, consider what happens here. Now, in the very first word in this example, you might have had these two words, the and he, being almost equally probable, but he is slightly more probable, so you chose he. Now, because you chose he, the word knows over here doesn't fit. And now that for the third word, the probability distribution is confusing. But on the other hand, if you had chosen the slightly less probable but almost as probable word the, then the knows is a very nice construct. You can actually be very certain of the third word. So having chosen a different word in the first time instant could influence the probabilities that turn up at the third time instant and affect the probability of the overall sequence that is chosen. So the point here being that making a poor choice at any time commits us to a poor future, but we can't know at the current time that we've made a bad choice. The influence may be way down in time. So how do we deal with this? Here's an alternate option. Instead of simply picking the most likely word at each time, you can randomly draw one of the words at each time according to the output probability distribution. We all know how to draw words from multinomial distributions. So you could just randomly choose one of these words and pass that on to the network to produce the next probability distribution and so on, and continue this till you get the end of sequence symbol. So in terms of the pseudocode, what this would mean is that the draw over here, the draw function we had over here, is now going to be replaced by a sample function which randomly samples from the output distribution. Once again, random sampling is not guaranteed to give you the most likely output sequence. So, and our objective is to obtain the most likely output sequence. So this is not a satisfactory solution. Although to be honest, sometimes this random sampling process can actually give you better solutions. In fact, often it can give you better solutions than the greedy selection of the most likely word at each time. So here we are. Making a poor choice at any time can commit us to a poor future and can give suboptimal outputs. So how do we deal with this? Here's how we deal with it. We don't choose. We're going to explore all options. So here's what we would do. Once you're done encoding the input, at the first time you would get a probability distribution over all words. Now instead of picking one of the words, you're going to clone the network. If you have V words, you're going to clone the network V times. And you're going to pass every one of those words to the network. So each word is going to go into a different copy of the network. So at this point, you would have V different probability distributions being produced by the network. Now, at the next time, each of those V outputs is again going to be, I'm going to clone the network again, starting from this point on. And then each of those V words is going to be passed back into the network to produce the probability distributions over the next word. So observe what's happening over here. At each time, we are starting with an SOS, and we are computing probabilities for W1, every one of the words in the vocabulary. So this is going to be what you would actually be computing is P of Wi given SOS and the input, right? Then from each of these, you're going to be computing the probabilities for every word in the vocabulary given all the words on the path, given all the words until that location on the path from the root of the tree until there. So here, for example, this is going to be the probability of W2 given SOS and W1, and so on. If you take this path, this is going to give you probability of W1 given SOS and W2 as the first word in the sequence, right? So if you go, because at each point you continue to compute the probabilities conditioned on all the words down the tree. If you just multiply all the probabilities until here, you would actually explicitly compute the probabilities for every word sequence. And then you can just pick the most likely word sequence. The problem here is that if you have an output of size v, after t output steps, you would have forked out v raised to t branches. And so clearly this is untenable. This is going to grow exponentially. Now we will introduce a heuristic. Instead of just continuing to grow every single branch, at each time we will retain only a subset of the branches, and we're going to prune everything else out. So for example, we might say I'm going to just retain the top k branches. So here, after the first symbol has been input, I have computed probabilities for all the words in the vocabulary. I might decide to choose only the 2 most likely words. And correspondingly, so I'm going to be choosing the 2 most likely words based on the probability of the words, the first word given all the input words. Now these words are now going to, I'm going to clone the network, and I'm going to expand the tree from just this small subset of words. But now if I have chosen only 2 words, I'm going to end up having only 2 times v branches out here. And each of these branches is going to produce the probability of the second word given the previous word on that branch and the input. So this is going to give you the probability of O2 given O1 and the input, where you're assuming O1 is he over here. These terms are going to give you the probability of O2 given that O1 is the and the input. And now the product of these 2 probabilities, meaning the probability here and the probabilities here, are going to give you the probabilities of this entire sequence of words until these leaves. And from those, based on this product, you would retain only the top k and knock the rest out. And so now we're going to have this pruned setup. And now these 2 can once again be expanded. And then at this point, if you multiplied all the probabilities until these leaves for each of these leaves, you're going to get the total sequence probability for the first 3 words for each of these leaves, from which you're going to, and you'd have 2 v such leaves, of which you're going to retain just 2 in my example. In general, if you decide to retain the top k, you're going to retain k. And you can continue to do this, and at each time, the criterion that you would use to decide which leaves to store is going to be based on the product of probabilities all the way from the root to the leaves. You would continue doing this until the most likely overall path ends in an end of sequence marker. Now, if you want, this is what you do if you want to just produce your one best guess. If you want to produce multiple guesses, then you can continue extending the other paths until they terminate in an end of sequence marker. Now, one little thing to watch out for is that sometimes, now because the end of sequence marker is itself part of the vocabulary, you might find, for example, that over here, the top k, the end of sequence marker is in the top k, but it's not the top 1 position, which means that although this sequence survived until here, the most likely sequence was this guy. So that means this, you cannot just output this as your most likely or your best guess for the most likely output. You must continue expanding the lower guy until you get a sequence that has terminated in the end of sequence marker, which outscores everything else that has been scored so far. So for example, if this guy continues, if this guy scores higher than this, then you'd expand these, and if after expanding these you find that this score is higher than these expanded scores, then you'd output this. Otherwise you'd continue expanding these until one of them hit an end of sequence marker. So here's the little pseudocode for it. I won't actually go through it in great detail, but observe what's happening. At each time you have some beam. Each path in the beam is now going to be put through a copy of the recurrent network to produce probabilities for all output symbols. And so you're storing all of these leaves in a list, and then you're pruning that list to retain only the top k. and those are the only ones that stay within the beam. And now at the next step, you're processing all of the paths within the beam. The pruning, of course, you find the highest score and retain just the top k leaves within the highest score. Now, this system, we see how it can be used to produce translations. How do you train it? Now, the model must be trained to make predictions appropriately. So, given I ate an apple, end of sequence, it must know to produce Ich habe einen Apfel gegessen. And so here's how you do it. You'd have a forward pass. In the forward pass, you'd input the source and target sequences. The output is going to be a probability distribution at each time over the target symbol set. The actual target at each time is going to be the next word in the target sequence. So when the input here is the start of symbol, start of sequence, you want the output to be ish. So this guy is going to be the target output here. So this is just like what we saw when we were learning the language model. And now you can compute the divergence between the sequence of probability distributions output by the model and this target sequence of words, which is just the input sequence shifted by 1. And that divergence, derivatives of those divergence can be propagated backwards through the network to learn all of the parameters of both the decoder and the encoder. Now, in practice, if you're using something like stochastic gradient descent, you wouldn't be computing the divergences everywhere. What one normally does is to randomly sample some of the output words and only compute the divergences at those randomly sampled words and propagate them backwards. So a typical usage, and often you choose only one word. So a typical usage is going to be to randomly select a training instance, which includes an input-output pair, the input English and the output French maybe, and you do a forward pass. Then from the output, you randomly choose one word and propagate that derivative backwards and update all of your parameters. So the overall training looks like this. You are given several training instances, input and output. In the forward pass, you compute the output of the network for X and D. Observe that when you're computing the forward pass, you're using both the input and the target output as inputs to the network. In the backward pass, you compute the divergence between the desired output and the actual output and propagate these derivatives of the derivatives of this divergence for updates. There's a common trick that's applied here. There are several tricks, but one of the most common tricks that's applied over here is to reverse the input order of the input. That's because the first word in the input is often most closely related to the first word in the output. So when you reverse the order of the input and provide the input in reverse order, starting with the end of sequence symbol going back to the first word, and then use the corresponding hidden representation to produce the output, then things seem to work somewhat better. Now this is just a empirical heuristic, and this has been, at least it has been reported to work better than simply providing the input in forward order. And once you do this again, back propagation is going to continue just as before. Now, this would happen both during training and during inference. So during training, you would be providing the input in reverse order, and the target sequence is going to be provided in the forward order correctly. During inference, again, you would provide the input in reverse order and then produce the output. So in this case, the overall training would look something like this. In the forward pass, you'd compute the output of the network using both the input and the target sequences, but now the input is going to be provided in reverse order. And then during the backward pass, you compute the divergence between the desired target output and the actual output and back propagate it to learn your parameters. So we've seen I've used machine translation as an illustrative example over here, but it turns out that this model can actually be used in many different situations. You can actually use this for machine translation. You can even use it for speech recognition. You can use it for dialogue. So you have maybe an input which is I have a problem, and the output is going to be how may I help you. Now they are both in the same language, but observe that the output really has no direct correspondence to the input. It's a completely different sentence. But the model must learn that when it gets an input like I have a problem, the output must be how may I help you. Or you can even use this for captioning pictures. We saw this as an example way back in the beginning of the class. I provide a picture, I want to generate a caption. You can use this model for captioning pictures. Let's see how. But before that, here's something important. What this model does is to encode all of the information about the input in the final hidden representation that's computed when the input has been completely processed. So you expect this hidden representation to somehow store all the information about the entire input sequence. Does it really do that? Sutskever and Vinyals have these very nice results in their paper where they first reported this model. These are all two-dimensional projections, I think using PCA, of this final hidden representation. And they've shown plotted the hidden representation for several example sentences. And you can see these are the representations for Mary admires John, Mary's in love with John, Mary respects John. John admires Mary, John is in love with Mary, John respects Mary. There are 6 different sentences, they're all very similar. Observe how they line up. That Mary expressing some kind of positive sentiment towards John, all cluster on this end. John expressing positive sentiment towards Mary, cluster up on this end. And the vector relationships too seem to carry from one group to the other. So also, I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. Semantically, these 3 are the same, but the word sequences are similar. And you can see how their representations cluster up. Similarly, she was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. These 3 are semantically similar. Again, they cluster up. So this representation does indeed seem to capture the information and the input in a reasonable way. And here are some examples of what they can actually do. This is machine translation. These are I think, translation from English to French. I don't know French, so I have no way of knowing if these examples are any good. But those of you who do, or those of you who have access to Google Translate, should be able to put these things in and figure out if the translations are indeed good. And here you must be warned that when Google Translate first upgraded its service, I believe that the model that they used was something based on this framework, which meant that Google Translate might indeed have just given you just exactly these translations. Here's a different example. This is something that we can understand. This is for a dialogue system from a neural conversational model by Oren Vinyals and Kwok-Kwok-Lei. And we're using the same model here, except the input is now some text input by the human, and the output is the machine's response. So both are in English. So the human says, the machine starts the dialogue. What is the error that you're running, please? The human says, I am seeing an error related to VPN. Observe the machine's output. What is the error message that you're getting when connecting to VPN using Network Connect? So see the appropriateness of the response. The machine responds, connection refused, or something like that. And now the machine actually knows to produce, may I know the version of the Network Connect you connect. So the output, this is not a system that knows anything about the actual problem. This is just a simple language to language, sequence to sequence conversion model, and it's producing very plausible dialogue. Here's the other one that I mentioned, producing captions for images. Now this is not really a sequence to sequence problem. This is more a problem of converting an image to a sequence of words, but it turns out the model is very similar. Remember what we had before? Here we had an encoder that in the model, so see the figure to the right for those of you who can't see my pointer. In the model you had 2 stages. First you had an encoder which processed the input, and produced a hidden representation. Then you had a decoder which used this hidden representation, produced an output. We are going to use a very similar structure over here, except that instead of using an encoder that processes language and produces a hidden representation, we now have an encoder that processes an image and produces a hidden representation. And this encoder could just be a very conventional convolutional neural network. So here's what the image captioning problem does. The initial state is now produced by a state-of-art CNN-based image classification system. The hidden representation, final hidden representation produced by this network is now input to the language generation system, which produces the sequence of words that caption the image. So during inference, here's what you'd be doing. You're given an image, you process it with a CNN, and you get a hidden representation. So this one is now fed as the initial hidden representation to the decoder, which now sequentially draws words and generates word sequences from the conditional output distribution, where at each time the word is drawn from the probability distribution of words given the image and all words output until that time. Now, in practice, the actual drawing is going to be done using beam search, as we explained earlier. And so this can continue until you produce an end of sequence symbol. So to train this model, you'd be given several image caption pairs. The image network, this image network would, in the implementation reported, is pre-trained on a large corpus of images like ImageNet. So thereafter, you don't modify it anymore. And then in the forward pass, you use this hidden representation to produce distributions at each time, given the image and the caption. Subsequently, in the backward pass, you give the caption as the target output, compute the divergence, and propagate the derivatives of the divergence backward to learn all the parameters of the network. You don't update the parameters of the CNN itself. You could, but this tends to be not be productive. So the actual caption generation portion model only updates the parameters of the model that actually produces the caption. So we saw these examples in the first lecture. Here are some captions that are generated. A man in black shirt is playing a guitar. Construction worker in orange safety vest is working on a road. 2 young girls are playing with a Lego toy. Well, they're not both young girls, but you get the idea. Boy is doing backflip on wakeboard. So now, of course, the appropriateness of these captions depends on how well the CNN actually extracts information about the objects in the image. So when the CNN goes wrong, you can get some strange responses, like captions like a young boy is holding a baseball bat, or a cat is sitting on a couch with a remote control. Or this is my favorite, a horse is standing in the middle of a road. I'm not sure where it saw the horse. But anyway, but you get the idea. It's a very simple model. This might have looked like magic when we started the class, but by now it must be apparent how it's actually very simple to implement. Now, in the models that we saw, we had one restriction, which was that the hidden representation produced by the encoder went in only to the first time step of the decoder. Clearly, that's not the most sensible way of, or the most optimal way of dealing with things. Intuitively, you'd expect that since the hidden representation stores information about every input word, it must be fed in to produce, it must be explicitly fed in when producing every single output word. And you'd expect that would work better, and indeed that is so. So here is a variant where this encoded representation is now fed in as to every single step of the output. So also if you are doing image captioning, this encoded representation could be fed in to every single stage of the output. These are all very simple variants. And here is an example where that variant is actually reported for captioning videos. So in this case, you have a sequence of images in a video. A CNN produces a hidden representation for every one of these images. Pooling layer averages all of these representations, and this representation is now fed in to every step of the decoder. And you can see the kind of captions it produces. A boy is playing a ball. So this is from this very nice paper, Translating Videos to Natural Language Using Deep Recurrent Neural Networks by Venugopalan et al. In June 2015. And here's pseudocode for it. The image initially produces some hidden representation H, which is provided as the initial hidden state to the network, which then goes ahead to produce captions. Now, the one key piece over here, how this differs from the machine translation framework, is that now at each time, so sorry, this is for the video. At each time, the hidden representation obtained from the video is also fed into the recurrent network. Now, what we've seen so far is what I call the simple model and several variants of it. There's a reason I called it simple. And the reason I called it simple is that in this model, all information about the input sequence is embedded into a single vector. The hidden node layer at the end of the input sequence is expected to retain information about an input about a sentence which could be arbitrarily long. So you're basically overloading the amount this poor node with the amount of information that it is supposed to store. Now, this kind of seems not quite okay, right? In reality, every one of these hidden representations carry information. And as you keep processing the input, this information could potentially, in fact will, get diluted downstream, particularly if the input is long. And what happens is that if you consider the output, different portions of the output actually relate to different portions of the input. So consider this English to German example. I ate an apple gets translated to Ich habe einen Apfel gegessen. Ich relates to I. Habe, now ate really actually becomes habe gegessen. So both of these two words, which are separated by two other words, relate to the word ate. Einen relates to an, Apfel relates to apple. So in order to translate Apfel, apple to Apfel, it makes sense that you want to focus more on the hidden representation after the word apple was processed than to actually wait until the end of the sentence where that representation might have been diluted by future words. So we need some way of figuring out which portions of the input to focus on while keeping in mind that the input and output may not be in sequential order. And case in point is this word ate, which actually became habe gegessen. So both of these should ideally be focusing on the word ate. Now, one simple way of trying to consider the appropriate portions of the input when producing any single output is to simply have explicit connections, right? But then we really don't have any way of knowing which word connects to which word. If you decide instead that I'm going to connect every input hidden representation to every output hidden representation, the number of connections is going to blow up. This will become highly over-parameterized. And moreover, this connecting every input to every output sort of beats the purpose because it ignores the actual asynchronous dependence of the input to the output. You're ignoring the fact, for instance, that Gegessen really wants to focus on 8 and not at something at the end, right? So to handle this, we come up with simple variation on the basic model, which is the attention model. Now, in the attention network, to illustrate what happens in the attention network, first I'm going to separate the encoder and decoder portions of the network. So this first portion is the encoder, this is the decoder, and here's how the model operates. At each time, the hidden hidden units of the decoder are going to get as input a weighted combination of all of the hidden representations produced by the encoder. So at time 0, for instance, the decoder is going to see as input, in additional to the start of sequence symbol, some weighted combination of all of these h's, and these weights are going to be specific to time 0. At time 1, the decoder over here is going to see, in addition to the hidden state as 0, some weighted combination of these hidden representations, where these weights are specific to time 1. So the weights with which the hidden representations of the encoder are combined to produce this what we will call the context input to this hidden representation will change with time. So again, observe that these weights with which these hidden representations are combined to produce the input at each of these output times vary with time. And so the input to the hidden decoder layer is a combination of 3 things. The input to the hidden decoder layer is going to be the previous word output, the hidden state value from the previous time, and the weighted combination of hidden states from the encoder. The weights, of course, are scalars. So these are all vectors. You're going to be averaging them, but it's a weighted average. The weights must be scalars. Now, how do we compute these weights? These weights must somehow magically figure out which words in the input to focus on. So in other words, when I compute a weighted combination of all of these hidden representations. So for example, let's say I'm converting English to German. So when ich habe einen, start Apfel, I guess. So when I'm trying to produce the word Apfel, this hidden representation must somehow know that H3 is the one that is most important, right? So you want these weights to be such that the weight for H3 is large and the weights for the remaining H's are somewhat smaller. Now, what is the process by which such a weight can be computed? Where is the information to be obtained from? So we're going to hypothesize that the information about which portion of the input to focus on is represented by 2 variables, is captured in 2 variables. First, these hidden representations themselves, obviously. We need to be able to, which hidden representation to focus on is a function of the representation itself. And also the hidden state value at the previous time. So to find out the weights with which these guys must be combined for time 3, we are going to assume that the weights are a function of S2 and the hidden states. So the weight assigned to the ith input at time t is some function of the hidden state computed from the ith input and the output state at time t minus 1. Now, we have another requirement. You don't want arbitrary weights. You want the weights to actually represent a distribution. When we want to compute a weighted average of the hidden representations of the input. Now, if you want to compute a weighted average, it means that the weights must sum to 1. In other words, the weights must represent a probability distribution. So you want a low, for example, if I'm trying to translate the word apple, then, or if I'm trying to produce the 4th output over here, then the network must know that the fourth output really must focus on the word apple, and you want weights of this kind which are low for all the other words and high for the fourth output. So, and all of these weights must sum to 1. So the weights are required to be a distribution over time. The way we will implement it is as follows. We are first going to compute some raw weight for each time. The raw weight for each time is going to be each input time. So the raw weight is going to be at for any input is going to be a function of the hidden representation of that input and the state at the previous output time. Now again, there are two different times we are speaking of over here, to be very clear. There is input time which I am indexing by I, and there's output time which I am indexing by t. So if I want to know with what weight the ith input must be considered when I am making the tth output prediction, then the raw weight is going to be a function of hi and the output hidden state as t minus 1. Now these raw weights can be any values. We are not really placing any restriction on them. But then we will convert these raw weights into a probability distribution by putting the collection of them through a softmax. You would have one raw weight for each output column. You would have one raw weight at each input time. These raw weights are going to be processed through a softmax so that you end up with a sequence of positive values which all sum to 1. And this raw weight itself can be computed using a variety of functions. Several have been proposed. The simplest one, of course, is simply to compute the inner product between hi and st minus 1. So that's assuming that these hidden representations and these representations have the same dimensionality. If they don't, then you can have a matrix inner product where the matrix does the translation of dimensions. You can also have other functions like this peculiar one with a tan h, or you can even have a multi-layer perceptron which takes in the hi and st minus 1 and produces values. There are different mechanisms to compute the raw weight, the most popular one. So popular ones are the first two. And then subsequently you can pass those through a softmax to compute the weights. So the overall process of inference is going to be as follows. First, you would pass the input through the encoder to produce hidden representations at each time. Then you compute the initial state of the decoder, and this is typically computed either from the final hidden representation of the encoder or through some weighted combination of the final hidden representation of the encoder, or even might be some fixed value like 0. And then if it's a weighted combination, then this ws would be a learnable parameter. Then in order to produce the first output, the first thing we would compute is a raw weight for every one of these input time instants, and that raw weight is going to be a function of the h's and the initial output state. So you would compute the raw weight ei0, which is because we are producing the 0th output, and that you're going to have one raw weight for each of these guys. From these raw weights, you'd apply a softmax to these raw weights and compute the normalized weights for each of these inputs. These normalized weights are going to sum to 1. They represent a distribution. And then using these normalized weights, you'd compute a weighted sum of all of these hidden representations. That gives you the z0, which we will call the context. And this z0 and the start of state symbol are going to be passed together to the hidden layers of the decoder, along with s minus 1, of course. And the decoder is going to produce a probability distribution over words for the probability distribution for the first word and the output. You draw a word from that distribution. And now, now that the first word has been drawn, we need to compute the second word. To compute the second word, we are going to compute raw weights once again for every one of these guys, but this time these raw weights are going to be a function of s0 and these h values. And these raw weights are now going to be passed through a softmax to compute the normalized weights. And these normalized weights are now used to compute a weighted average of these hidden values, which is the context, which is now fed in along with the word that we drew in the first time ish, to produce the probability distribution of the next time from which you draw a word. And then you continue the process in the same manner. So once again, you're going to use this S1 and these Hs to compute the raw weights for all of the inputs, and use those raw weights to compute the actual normalized weights for all of the at all input times, and use those to compute the context vector, which is now fed in to produce the next probability distribution. And this process is continued until you finally output an end of sequence symbol. Now again, as before, the objective of this whole process is to produce the most likely output that ends in an end of sequence symbol. So you want to produce the output word sequence which has the highest probability given the input. So you want to produce the word sequence for which the product of these probabilities is highest. Now observe that at each time I had this magic step where I said I'm going to draw a word from this distribution. Now if I just choose the most likely word at each time, this, as we saw, is suboptimal. Drawing something randomly at each time is also going to be suboptimal. So what we will do instead is to go back and do what we did earlier. We're going to use beam search. At the first time, we're going to retain all choices, and we're going to fork the network with every possible word as input. And then based on the probabilities of the words, you're going to retain some subset. Then that subset is going to be forked out again. And now based on the probabilities of the sequence of words until the leaves, you're going to retain some subset depending on the beam width, and that subset is going to be forked out, and so on. And you will continue until you produce an end of sequence symbol. And as before, you can either produce one output, or you can produce a sequence of best guesses, in which case after the best guess has been produced, you can continue to extend the sequence to generate other guesses. And again, as before, you can run into situations where you produce an end of sequence symbol that is less likely than some other sequence which can continue to be extended. So you must continue to produce symbols until you get a sequence that ends in an end of sequence symbol that is most likely. So here is the beam search, pseudocode for the beam search. I won't actually spend time on this, but do take a look at the code. Now, so a key component of this model is this attention weight. Observe that we actually computed a weighted combination of the hidden representations at the input. And the weights were produced, these weights are what we call the attention. And so at each time, we computed a different set of weights over the inputs. Ideally, you want these weights to magically sort of focus on the most relevant word from the input, or the most relevant set of words from the input, in order to produce the current output. Do they really do so? So let's visualize. So here are some examples from machine translation. In this case, English has gone in, and the attempt is to produce French. So the input sequence here is the agreement on the European Union Economic Area was signed in August 1992 period, and there's the end of sequence symbol. Now, of course, the encoder first produces the hidden representations for all of these guys. At the first time, you get a sequence of weights. So this first bar, the first column in this figure, is a visualization of the sequence of weights, and you find that, and the lighter it is, the greater the weight. And you find that at the first time instant, the largest weight is applied to the word the, and the corresponding decode is the word la. Now, at the next time, the weights, the largest word is to the word agreement, and it produces the word accord. So you can see how the weights actually sort of focus on the right input word. The most interesting segment over here is this. European Economic Area gets translated to Zone Économique Européenne in French. The order of the words changes, and you can see correspondingly that when you actually visualize the attention weights, the attention weights actually flip their orientation. So when producing the word European, which is the 7th word in the output sequence, it's actually focusing on the 5th word in the input. So also when it's producing the word zone in French, which is the 5th word in the output sequence, it's actually focusing on the 7th word in the input. So it's sort of so this figure, which we'll call the attention map, actually shows you how the output aligns to the input, and by visualizing it, you can make out that the model is indeed learning to focus on the appropriate areas of the input. You have several other examples, and in every one of these cases you see similar behavior. So here are some more examples from the original paper that reported this model, Bahdanao et al. In 2016. Again, I can't vouch for the veracity of these translations since I do not know French, but I believe that if you do, you will find that these are actually excellent translations. Now, how do we train the network? We've seen how the network can be used during inference, how to produce outputs. But then to consider training, we have to factor in the structure of the model itself and how information can be propagated backwards. So here is how you would train. In the forward pass, you would initialize all the parameters of the network. In the forward pass, you'd pass the input through the network, and these hidden representations are then going to be used to produce outputs. Now, in the forward pass, remember that if you were actually performing inference, at each time you would be drawing a word. But now, you're not going to be using the drawn word as the input over here. You would be using the actual target output sequence as input, exactly as we did for the simple translation model. And then we can compute the divergence between these outputs and the target output and propagate the derivatives of those divergences back through the network. Now, in the process, the back propagation, we already know how back propagation rules can be computed, and if you've gone through the slides on how to compute a derivative, you should be able to write the back propagation code for this model quite simply. One extra bit of complication over here is that in the process of propagating these gradients backward, you must also make sure to update the parameters of the attention function g if it has any parameters. Now, there are some tricks of the trade. What this figure shows is that when you are in the forward pass of training, the decoder actually gets the actual output word sequence as inputs. You can change that, and some fraction of the time you can actually pass the drawn words as the input. So for example, instead of passing Ich habe einen Apfel gegessen, for this third word you can randomly choose some word from this guy using whatever procedure that you might choose for random selection, and feed that input in over here and train the network. The objective of this is to try to force the network to learn to produce the correct output, even if some of the previous words were erroneously converted. So this mechanism is what we will call teacher forcing, which occasionally passes the system output as input during training. And this introduces some extra complications again, in that the process of selecting a word from a probability distribution is not a differentiable function. So we need some reparameterization using a technique called the Gumbel noise trick, which you will learn about in your recitation. There are various extensions to this basic model. Now, in the model that I showed the encoder processing the input left to right. But because the processing of the encoder is independent of the processing by the decoder, and because the encoding is performed first before you begin decoding, in fact the input can be processed bidirectionally. And so the most effective encoders are actual bidirectional networks, which process the input left to right and right to left. You can have variations on the framework, attention framework itself, whether you should be letting the decoder consider the entire input, or whether you want it to only consider certain portions of the input. So you have features like variants like local versus global attention, which is defined in this paper over here, and several other extensions. You also have now something called multi-head attention. In the model that we just saw, we computed a context vector Z, which was a weighted combination of the hidden representations from the input, but we computed only one context vector. What you could actually do is to compute these weights using multiple functions, and each of these functions will give you a slightly different weight, and you could compute the hidden different context vectors using these different sets of weights. And so now you'd get a collection of context vectors which you could feed into your decoder. So this process of computing different sets of weightings with which the input can be combined is what we will call multi-head attention, where the different weightings are computed using different mechanisms. Within each of these, we compute something called a value and something called a key. Again, you're going to encounter these in your recitation. And the different keys and values can be combined to obtain different weightings. I'm not going to spend time on this, we're out of time. But then once you're done with your homework 4, all of these will be very familiar to you. Now, attention-based models are currently responsible for the state-of-the-art in many sequence conversion systems, like machine translation, actually this is text in source language and text in output language, or even speech recognition. It turns out attention-based models are actually very good at recognizing speech, and they have this added benefit that because the output is not required to be have order correspondence with the input for attention models, you can actually use these to produce the spelling. You can have the output, you can have speech go in, and the output actually be a character level transcription of the input, which provides you the additional benefit that you don't need to specify a vocabulary of words. The recognizer itself figures out what the words must be and how to spell them. Here is a very nice result from image captioning. So again, the encoder doesn't have to be text, as we saw. The encoder could just be the input could be an image, and the encoder could be computing the convolutional could be a convolutional neural network computing a hidden representation of the image, and you could learn to pay attention to different portions of the image. So here is a very nice result from a paper called Show, Attend, and Tell from 2016, where they do image captioning using these attention models and observe how the attention learns to focus on the right portions of the image. This says the woman is throwing a frisbee in a park, and here is the attention map when it was producing the word frisbee, and see that it observe how it focuses on frisbee. A dog is standing on a hardwood floor. Observe, I don't know if there's a dog standing on a hardwood floor, but observe that when it's producing the word dog, it actually focuses on the dog's nose. A stop sign is on a road. Again, when producing the word stop, it actually focuses on the region of the image corresponding to the stop sign, and so on. So, in closing, this is, as I said, this is the last of the sequence of lectures on recurrent neural networks. We have introduced the basic notion of sequence processing and recurrence in neural networks. We extended this to sequence models, where We saw different kinds of sequence-to-sequence modeling problems, which are generalizations of recurrent neural network formalisms. And specifically, we've looked at the CTC framework, which deals with sequence-to-sequence translation when there's order correspondence between the input and output, and attention models, which can perform sequence-to-sequence translation when there is no order correspondence. There has been a ton of work in the area, obviously. So what we have covered in this class can only be considered somewhat of an introduction. So for details, please refer to papers on the net. We used to maintain a list of papers, but given the sheer number of papers that have appeared on the subject, I recommend that you actually look this topic up on Google Scholar and read some of the more cited papers. And if you have questions, as usual, you can post on Piazza. This is going to be, the attention models are going to be the focus of homework 4, where we will perform speech recognition using attention models. So hopefully by the time you're done with homework 4, you're actually going to be quite comfortable with the topic. Thank you.